Okay. These are the topics for today's class. About the first topic, let me show you one more example. Take a review about some formulas. The first formula is divide the difference and the loads x0, x1, xk. Here, I assume these loads are distinct. They are different. The formula is this. Divide the difference at x1, x2 to xk. Minus divide the difference at x0, x1, xk minus 1. And then divided by xk minus x0. Yeah, we will use this formula. The second formula is when the loads are identical, the definition of divided difference is here. There are k plus 1 x0. Then the formula to compute this divided difference is, let me see, is 1 over k factorial derivative of order k on function f, evaluate at x0. Okay, now let me present one example about this topic. Then I finish this topic. Example 1, under this topic, use the extended Newton divided difference method to determine a polynomial that takes the following values. The value of the polynomial f1 is equal to the function value f1. Function value f1, let me give some concrete value to it. Say it is 2. And derivative of the polynomial f1 is derivative of the function f1. Also, let me give a concrete value for derivative of function f1. I say it is number 2. Number 3. P at 2 is equal to function value at 2. Function value at 2 is, say, 6. Derivative of P at 2 is equal to function value at 2 derivative. The value is 7. And derivative on P at 2 is equal to function derivative, second derivative at 2 is equal to 8. Now, the question is how to find such a polynomial satisfy all these 5 conditions. Let me give a name to these 5 conditions. Star, okay, star. Call them star. Okay. Now, solution. First step is establish a new set of nodes. Okay. Now, this node, let me give a name. C0. And then this one, C1. This one, C2, C3, C4. Then the Newton interpolation polynomial in terms of these C nodes is the Newton interpolation polynomial in terms of the C nodes is this polynomial. This polynomial, the degree is 4. Degree 4 is sufficient because a polynomial of degree 4 has 5 coefficients. 5 conditions can completely determine 5 coefficients. Divide the difference of f as C0, constant term. Then divide the difference at C0, C1 times x minus C0. Then plus C0, C1, C2 times x minus C0, x minus C1. 1, 2, 3. Okay. The fourth term is C0, C1, C2, C3, x minus C0, C minus C1, C minus C2. The last term, C0, C1, C2, C3, C4 times x minus C0, C minus C1, C minus C2, then C minus C3. It turns out that this polynomial satisfies all these 5 conditions. This polynomial P is the desired Hermite interpolation polynomial. To the conditions in star. Now the next step is how to determine. The next step is determine the coefficients. This time, I use divided difference table to determine the coefficients. Let me make the following table. First column, list the nodes C2, C3, C4. Second column, difference, divided difference of order 0. Order 0 actually is function value. Brackets, not parentheses. The third column, divided difference of order 1. C1, C2, C2, C3, C3, C4. The next column, divided difference of order 2. Two. C1, C2, C3, C2, C3, C4. And then the next column is order 3. Last column is order 4. In this table, the top row consists of the coefficients of Newton interpolation polynomials. So our goal is determine the first row. Okay. Okay, now first column, just function values. Second column, how to compute second column? By the formula. Yeah, by this formula. C0, C1, CK minus 1, then over CK minus C0. Say for example, if I want to compute this entry, let me draw a triangle. Yeah, starting from this entry, let me draw a triangle. Yeah, triangle. And then here, triangle. Triangle. Okay, triangle. Triangle. Then this entry is equal to this entry minus this entry over this minus this one by formula. Okay, now let me plug in the values for C, for the C nodes. For the C nodes, let me see. C0 is 1, C1 is 1, then the other C nodes are 2. Okay, now let me plug in. Okay, this is a 1, 1, 2, 2, 2. This guy is function value at C0. That is function value at 1. Okay, so this is a function value at 1. This is function value at C1. C1 is 1, so it is function value at 1. And this is a function value at 2. Function value at 2. Function value at 2. How about this? Let me plug in the values for C0 and C1. C0 and C1. So 1, 1, 1, 1. And here is 1, 2. 1, 2. This guy is 1, 1, 2. 2, 2. This guy is 2, 2, right? 2, 2. And this guy is also 2, 2. Also 2, 2. Now here, 1, 1, 2. So 1, 1, 2. And this is 1, 2, 2. 1, 2, 2. And this entry is 2, 2, 2. Yeah, let me erase. the fourth column, the next column, 1, 1, 2, 2, 1, 1, 2, 2, and here is 1, 2, 2, 2, 1, 2, 2, 2, and the last entry 1, 1, 2, 2, 2. Function values are given. Let me see. Function value at 1 is 2. Function value at 2 is 6. So this table here, this is this is 2, and this guy is 2. This is 6, 6, 6. Divide the difference at 1, 1. Now the arguments are identical. Now this time I use this formula. Yeah, I use this formula. So 1, 1. So k is 1. So 1 over 1 factorial times derivative of f at 1. So this guy is equal to derivative of the function at 1. Derivative of the function at 1, let me see. Number 3. Number 3. So that is number 3. How about this? This is a derivative at 2. Derivative at 2, let me see. Derivative at 2. Number 7. 7. So this is a 7. Also, this is a 7. This is 7. Right? And this entry can be computed from this entry and this entry. So I temporarily don't compute it. How about this? This is there are 3 arguments by formula. By this formula, k is 2. So 1 over 2 factorial derivative twice at x0. x0 is 2. So this is a 1 over 2 factorial second derivative at 2. Second derivative at 2, let me see. Second derivative at 2 is equal to 8. So this number is 1 over 2 factorial times 8. It is 4. Yeah, this entry is 4. Entry is 4. Okay, now let me move to the next table. 1, 1, 2, 2, 2. Then the second column, 2, 2, 6, 6, 6. 2, 2, 6, 6, 6. Number 3, yeah, this guy is number 3. Then F1, 2. Number 3, F1, 2. 7, 7. 7, 7. Now, next column, 1, 1, 2. 1, 2, 2. Then number 4. 1, 1, 2. 1, 2, 2. Then number 4. How about this? 1, 1, 2, 2. 1, 1, 2, 2. 1, 2, 2. Then the last entry is 1, 1, 2, 2, 2. Okay, Now let me compute this guy. Draw a triangle. A triangle. Triangle. Okay. So F12 is equal to this number 6 minus 2, this number, then over 2 minus 1. 2 minus 1. It is 4. This number is 4. How about this number? Draw a triangle. Triangle. Draw a triangle. Then this number is F112 is equal to 4. This number minus the number 3. 4 minus number 3. Then equals to this number 2 minus 1. 1. Yeah, this number is 1. Yeah, this guy is 1. 1. For this number, draw a triangle. Draw a triangle. Yeah, triangle. Then we get 1, 2, 2 is equal to number 7. Number 7 minus number 4. 7 minus 4. Then over this 2. This 2 minus this 1. So 2 minus 1. Number 3. Yeah, correct. This is number 3. Number 3. For this number, for this entry, it is number 3 minus number 1. Then over this 2 minus 1. 1, 1, 2, 2 is equal to number 3 minus 1. Then over this 2 minus this 1. So 2 minus 1. So it's equal to 2. Yeah, this number is 2. Number is 2. And similarly, for this entry, draw a triangle. Yeah, triangle. Draw a triangle. Triangle. Then F122 is equal to number 4 minus number 3. Then over this number 2 minus this number 1. This guy is 1. 1. Then finally, for this, it is 1 minus 2 over 2. This 2 minus this 1. So this is 1 minus 2 over 2 minus 1. Negative 1. Therefore, I complete the divided difference table. The table is this. Therefore, okay. 1, 2, 2, 2. First column are the C notes. Then 2, 3, 1, 2. Negative 1. The first row are the coefficients of Newton interpolation polynomial. 2, 4, 3, 1. 6, 7, 4. 6, 7, and then 6. Now, plotting the entries on the top row, then the Newton interpolation polynomial is constant term is this number 2. Plus the second term coefficient is 3. X minus C0. C0 is 1. Then plus this coefficient 1 times X minus C0. C minus X minus X minus C1 plus 1, 2, 3. Now the fourth term 2 times X minus C0. C1, C2. The last term, -1, x minus C0, x minus C1, x minus C2, x minus C3. Now replace C0, C1 to C3 by their values. It is a 2 plus 3. X, the value for C0 is 1. 1 plus x minus 1. C1, the value is 1. 2 times x minus 1. X minus 1. C2, the value is 2. 2. So x minus 2. Then negative. So minus x minus 1. X minus 1. X minus 2 times x minus 2. Now simplify. We get this polynomial. This term x minus 1 times x minus 1 is x minus 1 squared. Then plus 2x minus 1 squared times x minus 2. Then minus x minus 1 squared, x minus 2 squared. Yeah, this is the polynomial that satisfies all these 5 conditions. The polynomial is Hermite interpolation polynomial to these given conditions. Yeah, you can have a check. Okay, yeah, you can have a check whether or not this polynomial satisfies the 5 conditions. Yeah. Okay. This is topic 1 today. I finished the topic with the example. Now we turn to study section 4, spline interpolation. Okay. A new section. Topic 2 today. Spline interpolation. Suppose we are given a table of values of some function. A table we are given. X0, x1, x2. Here I assume the nodes, they are different. Xn. Function value at x0 given. Function value at x1 given. And let me suppose P, this polynomial. Let P be the interpolation polynomial of degree not greater than n. Such polynomial is unique. Let P be the interpolation polynomial to the function f and the nodes. And also I assume, okay, also assume the nodes are in this open interval. Then we have a theorem. One theorem says that the distance of P, this polynomial, from the function f is given by this formula. 1 over n plus 1 factorial derivative of order n plus 1 on the function f. Evaluate at some point psi. Psi this point is also in this open interval. Then times the product of x minus xk. K goes from 0 to n, right? Do you remember that formula? Okay, where x and sine x both inside the interval. Okay. Now, in practice, usually we don't know function f, but function f usually is, even though we don't know function f usually is continuous and smooth. Smooth means has derivative, or its graph has no corner. Smooth. In practice, usually this factor derivative, usually absolute value of this factor is not too big. It's not too big. Okay, now there are two cases. Case one. When the interval AB has a length less than 1. Okay, because the logs are all in the interval AB. Let me draw a diagram. Interval AB. Now all the logs inside the interval. And also sine this point inside the interval. Inside the interval. X also inside the interval. Yeah, X also inside the interval. X as somewhere. So in this case, we can see that this product X minus 1 log in absolute value less than 0. So as a result, their product in absolute value less than 1. When n is large, much less than 1. So in the case when the interval is small, the length less than 1, the approximation of polynomial p to the function f very good, because this term, the error term, is very small. Second case, however, when the interval is greater than 1 in length, greater than 1. Second case, case 2. AB has a length greater than 1. In this case, the error may not be small, right? Say for example, the interval AB is, the length is 10. Say for example, say A is 0, for example, 10, B is 10. Then the logs is X0 is 1, x2 is 2, for example. Then x8 is 9, for example. Okay. Now this time, let me take one x. Say x is 5.5. Then in this case, x minus x0 times x minus x1, x minus x8 is a large number. All right? 5.5 minus 1, 4.5 times 3.5, 2.5, 1.5, then 0.5, and times 0.5, and so on. The last factor is 9 minus 5.5, 4.5, 4.5. Okay. So this number greater than 1, large. Especially when n is large, much larger than 1, then this product will be huge. As a result, the approximation of the polynomial to function f not good, very bad. So 2 cases depending on the size of the interval. When the interval, the size, the length less than 1, this approximation is good. But when the interval is large, a large interval, the approximation may not be good. Now the question is how to handle large interval. How to handle large interval. Yeah. Okay. When interval is large, the idea to overcome the difficulty is cut interval into subintervals. Each subinterval, the length less than 1. Okay. Divide AB into subintervals of length less than 1. And then over each subinterval, construct interpolation polynomial. So over each subinterval, we construct interpolation polynomial. Now, a natural question is, we have many interpolation polynomials. How to connect these polynomials smoothly? Okay, this is the question that we want to answer in section 6.4. Okay. All right. The question, okay, divide this interval into subintervals. Then construct one interpolation polynomial over each subinterval. We have many interpolation polynomials now, each over one subinterval. Now the question is, how to smoothly connect these polynomials. We will develop skills to answer these questions. The resulting effort is called spline interpolation. Okay. All right. Now I want to answer this question. Let me introduce some definitions. Definitions in mathematics are very important. Definitions. Number 1, What is a spline function? Okay, a spline function. What is a spline function? Here is the definition. A spline function is a piecewise polynomial function. Okay, precisely. Suppose n plus 1 point T0, T1, Tn have been specified. And suppose these points are in increasing order and satisfy in increasing order T0 less than T1, T1 less than T2, and so on. Yeah, Tn. Let me draw a diagram. Yeah, this line is x-axis. Now we have n plus 1 points. These points, we give a name to them. We don't call these points nodes. We call them not. Okay, not nodes. Okay. Now T0 here, T1 here, T2 here, Tn minus 1, Tn here. Now over T0, T1 construct a polynomial. A polynomial. Let me give a degree of this polynomial. Say, also suppose an integer, k, say k, k can be 0, but not negative, has been prescribed. Okay, now over each, over the interval from T0 to T1, construct a polynomial. Then over T1 to T2, construct a polynomial. Degree is k. Over T2 to T3, construct a polynomial. Over Tn minus 1 to Tn, construct a polynomial. Okay. Okay, now a spline function. A spline function of degree k with the knot T0, T1, Tn is a function. Let me give a name to this function. Say, according to the book, call this function S, the first letter of spline, such that So we want all the polynomials, we connect them smoothly such that as this function is in this set k minus 1 AB. What is AB? Suppose that AB, the interval contain all the lots. Say A is here, B is here, B is here. So S should be in the set. S should have derivative of order k minus 1 and divide on AB. AB, right? The second condition is B on each interval. Yeah, pay attention. This interval is closed on the left. Tk minus 1. Ti minus 1. Ti minus 1. Ti. On the right, this interval is open. On, say for example, the interval here, T0 including, T1 not including. So on this interval, S, this function is a polynomial of degree k. On each interval, S is a polynomial of degree at most k, less than or equal to k. Yeah. So if a function satisfies these two conditions, we call the function a spline function, degree k, with associate with these given lots. Yeah. So this condition says that globally, the function S can be, the function S is smooth of order k minus 1, can take derivative until order k minus 1, and order and also all the derivatives are continuous. Okay. Condition B says that locally, function S is a polynomial. Locally polynomial. Globally, the function should be smooth of order k minus 1. Then the function is called a spline function. The degree is k, associated with these given knots. Okay. I don't have time to continue. So today I only present the definition about what is a spline function.